I'm going to do two different examples of a base dissociation problem. In the first one, you are given the Kb for aniline and the initial concentration of 0.025 moles per liter. Notice aniline is here. Just like in the acid dissociation, if you want to write a generic B for a base that is just going to accept one proton, with water and then write Hb plus and OH minus, this works for your base dissociation. Aniline will accept a hydrogen and it would be C6H5NH3 plus with the hydroxide as your conjugate base. So if we initially start with 0.025 moles per liter and water will not have a concentration, there is no concentration of our conjugates initially, so these are plus X. You have an ice chart completed just like so that your Kb, remember that's the equilibrium concentration for aniline, a specific base. These are constants. You can look them up in various tables. So the Kb will be equal to x squared over 0.025 minus x. We have another one of these situations where the initial concentration and the Kb are different in magnitude by a factor greater than 3. Your concentration is times 10 to the negative 2, and your Kb is times 10 to the negative 10. So the magnitude difference there is 8. 8 is greater than 3, and thus you can ignore this initial change and avoid doing the quadratic formula. Let's rearrange this for x and plug in our Kb value. This would be x equals the square root of your Kb, 4.3 times 10 to the negative 10, times 0.025, all square rooted, giving you a final x value of 3.278719 times 10 to the negative 8. The x value here is your OH, and you're asked for the pH. So remember from grade 11 that the pH plus the POH is equal to 14. So that you'll have, if you can solve for the power of hydroxide, the POH in this case, you can rearrange that to get your pH. Since you don't have hydronium appearing as a product and you have hydroxide, you will not directly get the pH in these questions. So if we do the negative log, it's the negative log, the POH will be the negative log of the concentration of hydroxide ions, which is the negative log of our 3.278719 times 10 to the negative 8. And that value is 5.48429. Sorry, I'm reading my writing wrong. This was 3.278719 times 10 to the negative 6. And this is times 10 to the negative 6. And that makes sense why there's a 5 here. If you've done something wrong, just like that, that's a little check. Knowing it's the magnitude times 10 to the negative 8, and it's a logarithmic scale, this should be around 8. But now that it is corrected from my work before, this should get negative 6, and it is closer to 6 in this case. So that is your POH. And we can plug that into the formula here and go 14 minus the POH equals the pH. 14 minus 5, 14 minus 5.48429 equals your pH, which in this case is 8.5157. 8.5157, which to the proper significant figures is 8.5. And that's your pH for a 0.025 mole per liter solution of aniline. This makes sense. Aniline is a base, so the basic solution is above 7 for its pH. In the second example, you're given the Ka for the conjugate acid and the pH of a solution and the volume, and asked to find the mass of the initial reactant that would be required to create a solution with this pH. So there's a few things, and it's working backwards like some of the examples we did with gaseous ice charts. So the first thing we need to know, and this may be the first time we discuss it, is the Ka and Kb are two constants that, if multiplied together, when they're the conjugate acid base, Ka, Kb, you're going to get a Kw, which is the water constant. And that Kw is a constant, and it's 1.0 times 10 to the negative 14. If we think about this for a second, if your Ka was 1.0 times 10 to the negative 7, that would result in a pH of exactly 7. And if your Kb was the same, they would multiply together to get 1.0 times 10 to the negative 14. This means that if you're given a conjugate acid's Ka, you can find that base's Kb, since the ammonia and ammonium are conjugate acid-base pairs. Use the 1.0 times 10 to the negative 14, divide it by your Ka, 5.56 times 10 to the negative 10, to get that Kb. And in this case, the value is 1.79856. 79856 times 10 to the negative 5. And that is your Kb for ammonia, which will be required to find that initial concentration of ammonia in your solution. Notice here you're also working with hydroxide, so we need to do the same thing that we did in the last question. Just convert your pH into your pOH. That's 14 minus 9.22, which is 4.78. Could probably do that one in my head. 4.78. The pOH will give you the concentration of hydroxide with the formula that concentration of hydroxide is equal to 10 to the negative pOH. This is the same as what you would have done with pH, where the concentration of the hydronium ions would have been 10 to the negative pH. So 10 to the negative 4.78 equals 1.659 586 times 10 to the negative 5. This is the concentration of OH minus at equilibrium, at the final solution with your 9.22 pH. So writing our ice chart, we're going to use A for that initial value. I'm going to separate it here just so we see. Water does not have a concentration. This is going to be minus X. You're going to start with none of your conjugate acid or conjugate base. They're going to change on a 1-to-1 ratio with your reactants, so that your expression is Kb equals X squared over A minus X. Your concentration of OH is equal to your X. Your Kb is what we found here. So these two values can be plugged into this formula to solve for A. Rearranging it, you would have A equals, and then X, 1.659586 times 10 to the negative 5 squared over your Kb, 1.79856 times 10 to the negative 5, plus X So 1.65956 times 10 to the negative 5. Write all of that out, and your A value is 3.19096 times 10 to the negative 5 moles per liter. Now you are asked for the mass that would need to be added to a 500 milliliter solution. So we're just going to convert back to mass. We have concentration. Let's multiply it by our volume, which is 0.5 liters, to get 1.595, 468 times 10 to the negative 5 moles. And then multiply that by your molar mass of ammonia, which is 17.03052 grams per mole, to get your grams. And that's going to be 0.272 milligrams. You're going to get it times 10 to the negative 10 and then multiply by 1,000 to convert it to milligrams. And that is your final answer. So a few different things probably brought up for the first time in this question. The constant water product is 1.0 times 10 to the negative 10. And if you have conjugate acid-base pairs, the Ka and Kb value multiplied to each other will always get 1.0 times 10 to the negative 10. Working backwards, if you're given the OH concentration or the H3O concentration for an acid dissociation, you can find that from pH or POH, plug it into your ice chart, and work backwards to find the initial concentration. And then we just did some grade 11 unit manipulation to get from concentration to mass, and 0.272 milligrams was our final answer.